By Harold
conference
on the night skies of Botswana, and I'm sure Harold will have something very interesting to present to us. The clouds are clearing up, and so this will be very interesting to listen to. Thank you, Harold.
Thank you for that introduction, Gihan. I'm going to talk about what's up on the night sky and actually in the early morning sky. But what really gave me a lot of excitement when I did some research for this talk was that we'll be able to see Venus during the day on the 24th of March very easily. So we'll spend a little bit of time on Venus. So interesting dates this month regarding the moon and the planets. The good news is Venus and Jupiter will be close to each other in the evening and Mercury and Saturn in the morning. The bad news is it will be very difficult to see them because they'll be close to the sun. Sorry about that. Full moon 7th, last quarter of the moon the 15th. March, the equinox, that's the start of autumn. Get out your jerseys. The good news there is that with autumn and then winter, we'll have many more clear skies at night. We're thankful for all the rain we've had, but it does mess around stargazing. Then new moon on the 21st. The 24th, the moon occults Venus. So those with sharp eyes can see Venus between about 10:15 and 11:25, can see the moon occulting Venus. So anywhere in South Africa or Southern Africa at about 10 o'clock, you should be able to see Venus with the naked eye right next to the moon. And after 11:30, you should see it on the other side of the moon. So I actually was quite excited. It's not often I've seen Venus clearly during the day, but it is the second brightest item in the night sky. So it's nice to see it during the day together with the moon. I'll dwell a little bit more about that now. That's just to give you a size, a relative size. On the left is Mercury, then Venus, then Earth, and then I can't see it behind you, but I think it's Mars. So in the left-hand, upper left-hand picture is Venus covered with clouds. Those clouds consist mainly of sulfuric acid. And I'm talking about Venus because we can see it. And I want to give you a little bit of background about Venus. On the right-hand side, the images taken by the Magellan spacecraft, and the Magellan used radar to get information about the surface of Venus, which we can't see because of thick, cloudy atmosphere. So let's just talk a little bit about the clouds and Venus. It's unusual. Venus is unusual because it spins in the opposite direction to our direction. We go anti-clockwise. Venus spins clockwise, but very, very slowly. It spins so slowly that actually 1 year on Venus is shorter than 1 day. It's believe it or not. A day on Venus is a little longer than a year on Venus. And so it takes some getting used to, because it takes 225 days, our days, for Venus to go all the way around the sun, but 243 Earth days to spin around just once. So it's something to get your mind around, that they measure time in years rather than days. And the sun rises every 117 Earth days. So it rises twice during each year on Venus, even though it's still the same day on Venus. Now, the other thing is, because Venus rotates backwards, the sun rises in the west and sets in the east. I'm going to be a little bit chauvinistic and say that's probably why Venus is regarded as a woman. Does everything opposite, but I won't get too controversial. But I found that very interesting. On the right is a very interesting graph. It shows the atmosphere extends up to 100 kilometers above Venus, and at 100 kilometers above, well, a little, near 100 k's above Venus, the clouds move at 100 meters a second. That means in 4 Earth days, the clouds circumnavigate Venus. It's an incredibly high wind that takes these clouds around Venus, which is just slightly smaller than Earth. Then, but that's right at the 100 k's from the surface. But right at the surface, the winds are very, very slow. So there's a gradual dropping down. The temperature also is amazing. That the temperature 100 k's up is about 100, if I interpolate, it's about 170 degrees Kelvin, which is about 120 degrees, minus 120 degrees Celsius. But right at the Earth's surface, which I can't see behind the pictures, but I remember it's over 400 degrees Celsius. So it's incredibly hot, and it's incredibly hot because Venus is so close to the sun. I just thought that might be of interest. So let's now get back to what's up in the night sky. Bright stars in the early evening in March. Crux and the pointers are low in the south. We spoke about Carina last month, and Canopus, you remember, is Alpha Carinae. That's prominent high up. Achernar is lower down to the southwest. Fomalhaut is closer to the west. Sirius and Orion are brilliant in the north. And Orion is slowly going to move away because that's a summer constellation and is going to be replaced in a month or two by Scorpius. Sirius, of course, is the brightest star. The Orion Nebula can be seen with the naked eye, and you should take the chance before it goes, bid it farewell, to have a look at Orion Nebula. And Venus shines brightly in the west early in the month, but later in the month, and the 24th, as you know, it's covered by the moon. Bright stars seen before sunrise in March. Crux and the pointers are in the southwest. Achernar is now towards the southeast. Scorpius is high overhead. Arcturus, Vega, and Altair are towards the north. And Saturn becomes easier to see each morning. Why I've done the sunrise sky is because I know David Slater goes out early in the morning and he looks at the stars. And so this is especially for David's sake. So he knows what's there and he won't get lost. Remember, visibility is better when one is far away from city lights. And what I've done here is I've just shown you the 2 books which I use as references. They could be identical, but they complement one another. The Sky Guide includes a lot of general information on the night sky, stars, constellations, dwarfs. And the picture on the Sky Guide is Pleiades. And you remember from last month's talk where Pleiades is? It's at Theta Carinae, which is part of the false cross. And the Collins Guide, I like that because it gives a detailed sky map for each month and looking north and south. It's a very useful little guide. So I can strongly recommend both of those. And with that, I end my talk with a little bit of time to spare.
Thank you very much, Harold. Very interesting and very informative.
But I don't know how to get out now. Here we go.
We have 5 minutes more before the main presentation. Are there any questions that anyone would like to ask Harold?
They must have blown their minds because of Venus.
Still in shock to
Yeah.
listen to all those stats that you-
They're trying to work out how a year can be shorter than a day.
Yes.
Harold, if I may, David Sykes here, do you use binoculars or a telescope, Harold?
I found binoculars are far easier than a telescope. A telescope, at my age, a telescope is very difficult to set up, David. And yeah, it's got to be able to follow the object in which you're concentrating. I've just found that very awkward. And I'm talking now in the midst of very serious stargazers, so I don't want to put my foot in it too much. But as an amateur, it's far easier with binoculars. What's better is if you're out there with your partner, and your partner can shine a strong laser where you're looking. That really does help. So you have a laser allied with your binoculars, if you understand what I mean.
No, absolutely. No, that's useful. Thank you, Harold. Yeah, we are surrounded by people with telescopes here. So also we are learners and beginners. So we're with the binoculars for the moment. Thank you, Harold.
Okay. I think Stuart Morongwe has got his, he hasn't muted his speaker.
Okay.
Hello, Stuart. Do you have a question for Harold? Motsopse, I think we are on time to make your introduction for the main presentation.
Thank you very much. I welcome everybody. It's quite impressive to learn that there are, well, right now 28 participants. So you are all welcome to this presentation. This is the Astronomical Society of Botswana monthly presentation. So it seems like we are kicking off the year in style, if I may say. Well, I'm very pleased to introduce tonight's presenter. She's not at all a stranger to the ASB. I think just after I joined, she made a presentation, and this was on astroseismology, a topic which is very of great interest to me as a geologist. And so I think she's got some good stuff for us today. So it is my pleasure to introduce Dr. Ceren Ulusoy. And today she's going to talk about a zillion carats of diamonds in the universe, which I think is another topic of interest to geologists. So thank you very much, Ceren, for keeping us on our toes. Ceren is, as I said, currently she's at the BUST, the Botswana International University of Science and Technology, which is located in Palapye. So, and there she is a senior researcher, senior lecturer in astrophysics. So that's what she does. She has, she has been, she studied her BSc, her master's, and a PhD at Ege University. I hope I'm not pronouncing this word correctly. Hello?
It's Ege.
I'll go with Ege. Okay, so so there we are, Ege University. This is in Turkey. And she completed her PhD in 2008. And then did stints with the National Research Foundation of South Africa, postdoc. Firstly at the University of Johannesburg for 3 years, working with the Kepler satellites, targets of the Kepler satellite, doing photometry and spectroscopy. And then did a stint with the University of South Africa, working with the Hubble satellite, and I'm sure other data. So she also has been visiting scientists at Canary Islands and Poland. Yeah, she also has worked for some years, 3 years, I think, as a director at the School of Aviation at the American University of Cyprus. So that's what she has done in her career. And I think she's going to really keep us on our toes tonight with her presentation about diamonds. So over to you, Ceren.
Yes.
You can start your presentation.
Yeah, just thank you. Can you see, just everyone just sees my screen, by the way, just like let's get a confirmation.
Yes.
Yeah.
Okay. So firstly, good evening, everyone. And first of all, I'd like to thank organizers actually just like of this meeting and for inviting me here today. And this will be my, just as they say, just a second presentation at ASP. So it was almost 3 years ago. It was physically, but before COVID hit and after COVID hits. And just right now, I'm going to be just presenting to the tiny lens. I hope delivery of the topics and contents will be successful. So for those just like who I haven't met yet in Botswana, just like let me just give little just a one sentence introduction just of myself. So I have a PhD. I can say just in the astronomy, space sciences, and would focus on an observational astrophysics. I'm currently just working as a senior lecturer in the physics and astronomy departments at BUST. So, like my name is Ceren Ulusoy, like in English pronunciation is Sibat. And can you hear me, by the way?
Yes, we can. Yeah.
Oh, okay,
Yeah.
Thank you. And also just like I would like to thank all of you exactly who is actually just like having time and participation in this meeting, and I appreciate all of you. And I'll do my best actually just to make the best use of the time just given to me. And the question is like after my welcome slides, and let me actually just like present. And my title is Zillion Carats Diamonds. I didn't make up, and it's a true, it's a real, and it's an observations just confirm that it's there are diamond structure in space rather than that we know just like they exist on Earth. And why I exactly just choose this topic, because I know that many of you and then most of the audience just among you and even me, we like actually hearing the galaxy mergers and supermassive black hole like the Sagittarius just like located in our galaxy center, and it's very fascinating and interesting to hearing them. But I'm including myself even just like when we see the first images coming from the that black hole pictures and images from the satellites, it's really fascinating and lots of questions comes to the mind. But I can say why I just like, this is white dwarfs. These diamonds are called as white dwarf stars. They seem exactly just ordinary targets, but that they are not ordinary targets. They are exactly extraordinary targets, because if you compare with black holes is just 600, they detected the oldest black hole as a 600 million years, but the ancient black hole age and 13 billion, that 13.7 or just a 5 billion years old. So in Cygnus. So which means that these are really ancient targets, and these are really archaeological space laboratories and cosmic chronometers and forensic laboratories and even cosmic laboratories. That's why I would like to just take attention to on these unique targets. And also they have got exotic stellar interior mechanisms that we are not used to know that exactly that stellar evolution theory like as other stars, because they are just simply that cold stars, and they show really unique specific features. So let me get through you just like my outline. So my outline, first I would like to talk about the star's definition, and then criteria about just being a star and working principles of the stars. So I would like to remind you, like who is not interested in astronomy exactly, to give it just a short generic info about it. Then we'll just talk about how stars just evolve according to their mass. Stellar mass is because it's the reference point for evolution, stellar evolution theory. And interior mechanisms is going to change, such as like proton-proton and CNO and triple alpha reactions. It's gonna just determine their endpoints. So also I'll mention about stellar life cycle and stellar classification, and just we are gonna come through white dwarf stars. And recent, then HRD diagram, and where white dwarfs are just on HRD diagram, and what is the significance of these HRD diagrams, especially recently, the latest stellar satellite missions and space missions has changed astronomy forever. Then I would like to take your attention on it, on HR diagram. So main characteristics, significance of white dwarfs and interior stellar structure in white dwarfs. And as I mentioned just a while ago, there's exotic mechanism and their diamondization process. So there's the diamondization process, they are just a cooling off and nuclear reactions just stop, but they start shining, but with a different mechanism. It comes to this. So,
Ceren, sorry, Ceren,
yeah.
do you want to hit the play from current slide button on the top left so this current slide fills the screen?
Sorry?
Do you want to hit the play from current slide button on the top left so it so it fills the screen? Sorry, yeah. There you go.
Yes. I'm sorry about it. So, oops. Yeah. So what is happening in this just this slide, okay? So we see exactly here, and there are in the just like in the past, and people just look at the night sky, and they have actually seen and some patterns. And these patterns, exactly, they made up stories regarding these patterns. But of course, these are the point targets and the point sources that the people just like saw in the night sky. As I say, this is Orion, and you can see, and it's a hunter, and a Canis minor, and a Canis major, and also just a Lepus here. Then, which means that we see the stars in naked eye, but some of them is dimmer, some of them is larger, some of them is just red and cool, and that you can't define cool, and we can just see the colors, temperatures, which is related to directly the temperature, but it's a physical fact. In the past, people didn't know this, and they didn't feel the characteristics and physical properties of the stars when they just making up stories And for example, the Canis minor and with the Canis major, a hunter is just hunting the Taurus. These are they try to make up stories in between the constellations. These patterns is called as constellations, of course. So this another one, sorry. Like with the exactly this a high-tech technology, and as we just like start learning space missions and just improved telescopes, let's say the lots high-tech telescopes, let's say James Webb and the new generation telescopes like James Webb and Hubble Space Telescope, we can exactly see what is happening in that. Just we could see at the center of the galaxy. So this is the center of the galaxy. How did you actually just spot the center of the galaxy? And with the naked eye, you know the Milky Way from the south, just like north to south, and it runs through the south to north to south, sorry. And there's a Sagittarius constellation here, just like I put there's an illustration here. So if you exactly just is like a T-spot, and then is the asterism here. If you follow this asterism, you're gonna just find, and it's a very bright region, and just next to bright region is there's a center of the galaxy where we exactly saw the picture of the center of the galaxy. Sagittarius A picture that we fascinated with the picture. In the past as well, from the patterns that we could see, like that we could see what is happening in our just the center of the galaxy. This is the most important thing that I would like to emphasize. Yes, then can we just we can zoom the center of the galaxy, and then we can see right now the physical characteristics of the stars. Why is it like a jewel box? So why is a jewel box? These stars are just colorful, and then which means the temperature, and then we can see the stars with the different colors here, and white stars and red stars and blue stars. We are just zooming the center of the galaxy with Hubble, and we can see what is exactly, it's a variety of stars and star regions, star formation regions, even just so we could see. So what is exactly happening in the galaxy? So I would like to first give a short definition before we go to white dwarf stars. And we illustrate the stars exactly like a polygon, or maybe pentagram, just a 5-pointed edges like this. This is how you illustrate and how I illustrate the perception if I just put an asterisk. And then second, this is one illustration, and second, real images are here. This is ESA, European Space Agency, in the middle, and the image taken. And then after that, the Solar Orbiter mission. This is a different one. And this mission is because what we observe is a pointy target. It's the all point sources. We can just see dots in the sky. But what we see in the reality with the Solar Orbiter mission and laboratory, let's say, and this is the star. This is in reality just exactly what is happening in the sun, our sun. So as I remember you, in one astronomical unit is equal to 150 million kilometers. So this solar orbiter just is the closest approach is here, the 42 million kilometer away, just this photo is taken. This is amazing. So to become a star in the space, International Astronomical Union, and there are some criteria. So firstly, it should be, of course, you should be in space and a celestial object. The first, you just a celestial object radiates energy from an internal source like nuclear reactions. It should produce its own energy. So it should be just bounce its own gravity. So this definition doesn't mean that spherical object that is going to be defined as star. No, because this definition excludes objects like planets, comets. Why? Because they can't even just provide the first criterion, that internal source. They don't have an internal source. So like I can just like I would like to mention about these two pictures. It's amazing. And one of them is just taken just with Hubble telescope, the other one the next generation telescope in the infrared. Hubble just use UV, and then Webb is using infrared region. What we cannot see in this here, these objects and galaxies are not appearing here. So this is this picture is like 83 million megapixels. So this is amazing. So how stars work is there are four main things, like this, they should keep the spherical shape, hydrostatic equilibrium, gas and radiation pressure must be balanced. So when just gravity and pressure, if the balance, stars doesn't collapse. And it also just it must be thermal equilibrium. This is the physics behind it, and energy generated must be equal to is according to thermodynamics. And thermonuclear reactions, why thermonuclear? Because if nuclear reactions happen, hydrogen burning like 4 proton here, so it's 1 helium. So it's a transformation. So energy transport is different mechanism, convection, either convection or radiation with different stars. This is the hydrostatic equilibrium. So the gravitational force in the stellar matter, in the core of the stellar matter, is Gauss inverse balanced by the pressure force. That's why this is the formula. All the physics students are very familiar with this formula, and I hope so. And this is the exactly just like keeps avoiding collapsing to collapse a star. Stellar structure is not that simple that I am just right now just easily just talking, and it's like talking just nonsense, but it's not nonsense. But to become a structure, to build a stellar structure, you need to just like know mass continuity, and you need hydrostatic equilibrium, energy conservation, and energy transport equations. And I can say during my BSc, it's a 2-semester course that is stellar structure equations to be able to understand. And I can say still people don't know about the stellar evolution, because each like year, each decades, and everything is changed with the satellite and space missions that we know. Also, you need to just build 7 unknowns: luminosity, density, pressure, temperature, and how opaque of the atmosphere. This is also, you need to consider just to build your model in precision. So there are just different types of stars, and sun-like stars, red dwarf and blue giants are here. This is a radiative zone, is a massive stars that have radiative zones, and inside, and convective zone is outside, and sun-like stars, a convective zone is outside. As we know, the sun flares and stochastic oscillations on the surface of the sun with the 5 minutes periods also important, and radiative zone is just inside the sun-like stars. So red dwarf is a completely convective zone. Sorry. So these are the nuclear reaction types of the nuclear reactions, like according to masses, based on the masses of the stars, and massive stars like the 7 solar and sun, more or less like average. They do carbon, nitrogen, oxygen cycles, and the other ones, and then proton cycles. And also the massive, another cycle is a triple alpha reactions. So these are the 3 reactions exactly, and then proton, and CNO, and then triple alpha. So for hydrogen, it's just like product is helium, the other one is a product is oxygen, the other one is beryllium. And also just like neutrino and gamma radiation is releasing from these reactions, which is crucially, just like emphasizing, I'm saying they're crucially important. So what is happening in the stellar life, just as a stellar life cycle? So what's exactly just a white dwarfs, or how they actually become white dwarfs and supernova and giant? There are luminosity losses, exactly. And these luminosity classes also gives us different types of stars. For example, supergiants and giants and subgiants and main sequence stars like sun-like stars and white dwarfs. These are the stellar cycle, and all stars and stellar nurseries, just like these are the star formation regions, and then these regions are distorted by some external forces, and also just gravity distort them, and they become supernova. So exactly the remnants of supernovas and other stars is just giving life to new stars. You can see different masses and also just what is like their end and beginning points. So for example, the sun-like stars is going to be red giants and planetary nebula. Then after that is going to be white dwarf, then the eternal darkness and dark, just like dark black dwarf, sorry. And then they are not going to be shining anymore, and we can't even know, we can't observe that their dwarfs, black dwarfs are going to be exist even in the universe, because there's no light. It's just that we can't get it. Sorry. So this is another illustration and animation, and you can see how just step by step from stellar nursery that I already summarized the previous slides, and after protostars. And when I would like to say just when exactly stars and life of the stars, when the nuclear reactions just start inside the core of the star, and the star starts exactly its age, so it's aging. So it sits on the main sequence. And then turn of points means that for example, for sun-like stars, if hydrogen just like ends, one turn of point is starting. So you can see also different main sequence, from star forming nebula, and what exactly happens to the star. So low mass stars mostly just becomes white dwarf, and massive stars and neutron, black hole stars, with a different of the type endings exactly. Yes, those just HR diagram. What is HR diagram? In 1913, and Henry Russell and Ejnar Hertzsprung, they made it just work. This work, they exactly just mapped the stars with the distance and the luminosities, and they saw that all the stars exactly just locating on a diagonal line. So, which means that this is something, these stars is acting in a just like familiar way, and what is happening exactly in this diagram is called as HR diagram. So it tells us life, death, age of the stars, as well as how far they are. So there are two relationships, mass and age, of course, and the mass determines the age of the stars and how long is going to be alive. More massive stars and die young, and less massive stars and just like white dwarfs is going to be ancient. So this is Hertzsprung-Russell diagram in astronomy is our periodic table. So because it's a luminosity versus spectral classes, Morgan-Cannon spectral classification, so it tells us exactly stellar temperature, effective temperature. And we can see exactly here what is happening, the different mass of the stars and sits on the main sequence, and they exactly acting differently after a turn of points. The main sequence stars is like sun-like stars is going to become just a red giant. Then after that, planetary nebula, and then we are going to see the white dwarf stars. There are also different groups of stars on the HR diagram. And just well above the main sequence, there are just a group of stars which are just massive stars, and the other ones exactly just the instability strip and the pulsating stars. So these are the steps of the stellar evolution. So as better telescopes were built, and I'm just like repeating this, more and more stars were observed, which means that we are going to just like dot, point more dots on this HR diagram, which means that as I can just like see, sorry, on the diagram. So evolutionary track of a M sun, our sun is going to be just like its evolution is going to be like that, and it's going to end up with a black dwarf, let's say, yes, and after white dwarf, after maybe 15 billion years later, because even our universe is 13.7 billion years. But I'm going to say a different fact. Still, we don't actually just like, there is no completed white dwarf exist in the universe, because it's going to be just more aged than universe that we don't know. That's why still there's no completed white dwarf, like we can say. And also with this knowledge, I would like to just like show you the Gaia DR2 data Gaia mission. This gives us an excellent animation as a real dots, and this is a filtered sunlight stars, and they did this animation with the same masses and luminosity and exactly same chemical composition they used, and they saw and how our sun is going to be just like act this evolution. And then 8 billion Kelvin is going to, temperature is going to be up, and after that 8 billion years later, sorry, then after that 5 billion years later is going to be just a white dwarf. After that 2 billion years later it's going to cool off, and then it's going to turn to black dwarf. This is amazing. So this is the old HR diagram, and as an astronomer, actually I'm fascinated by this Gaia diagram. Why? Because this is Hipparcos data, and only this these number of the stars is 120,000 stars, and here 1.7 billion stars, exactly just like dots on this diagram. So this is a Gaia just filters. BP is going to be re-red. It's not the same, sorry about it. And then we can see what exactly changed with the Gaia. If we zoom the white dwarf area here, we're gonna see exactly the full sequence of main sequence and full sequence of just a white dwarf band here. So even we can see just an unobserved white dwarf here, and also we can see just like here even full shape of red clump and red giants, where the red giants are exactly gathered, and upper side of the main sequence, exactly what is happening. So this information is really crucial, and then it's changing astronomy forever. And what happened to HR diagram? Captured unobserved paths of white dwarf's branch and shape of red clump, and this is 1.7 billion stars. Even recently, and 359,000 white dwarf candidates, thanks to Gaia data, is just listed and released as well. So what are white dwarfs? We also just like say, this is the end point of stellar evolution. So sun-like stars, let's say less massive stars, are the final remnants of low and intermediate mass. Exactly, it is estimated that the initial mass is going to be 10 plus 2 m sun, but upper mass limit is not known well. So it means that over 97% of the stars in our galaxy are going to be white dwarfs. And typical ages is 1 to 10 giga a year, and extremely cold and ancient objects. So as I just also said, like Gaia DR3 data release and 359,000 white dwarf candidates also presented. And if you are interested, you can actually go to Facilo et al. Publication. And a white dwarf just the size exactly is like our Earth. So, but I would like to take your attention about the densities. Look at just the Earth density, and then look at the white dwarf's density, which means that is about the M sun. So there's one question from me. If a white dwarf enters a solar system, what's going to happen to us? So do you think it's not going to happen anything else because of the gravity? This is gonna just mess up all solar system, because it's, remember, there's an M sun, and remember this gravity and density inside. Why they are essential? So we have to actually just like study on them really seriously because they are excellent chronometers, cosmochronometers, and nucleocosmochronometer means that as a radioactive decay of the elements from the primordial and Big Bang time, Big Bang universe, if you study on them, you are going to just detect like age, because age and mass and is directly related to each other. If you just like detect the oldest white dwarf in the universe, you are going to just to know about the universe age. So also there are ultramassive white dwarfs relevant. Why? Because they are also neon oxygen, and their mechanism totally just like behaves differently from carbon over oxygen ones. So ultramassive white dwarfs also just like thin hydrogen layer, and they are pulsating, and they're just a classification is a astroseismology comes to the scene. So it's amazing that and what nuclear reactions and stop and starts just like giving us a last heartbeat before the eternal darkness. So also we can study on with the pulsating and with the astroseismology inside the layers, and with the forward Yöntem is a specific with the forward method, is a specific method. And it's a final fate of planetary systems, and with the Chandrasekhar limits. The Chandrasekhar limit, it's at most, it says that a white dwarf mass must be 1.44 m-sun. So which if beyond 1.44 m-sun, which means that the mass is going to collapse, it's not going to be white dwarf, it's not going to just like keep its shape. So it's also why they are important as a post-main sequence. What is post-main sequence? A red giant and pre-white dwarf and AGB, asymptotic giant branch evolution is important. We determine what's going to happen to white dwarf. Is going to pulsate, or is going to just a cooling off, and how long is it going to take? These are the questions. So also a white dwarf evolution as cooling anomaly is important. And then recently, and one more discovery that I'm going to present, and with the animation, what is happening exactly. And there's some group of white dwarfs of and it's a piling up of one specific region, and they are delaying their cooling. It means that they are enjoying just like slow aging process, and they look like younger. So this is also important. And also, sorry, so this is the white, what is happening? It's acting up. Okay. Yes. So white dwarf is a degenerate dwarf, which means that ideal gas laws are not working and running inside the star anymore. And white dwarfs occur both single and in binary systems. The binary systems and supernova just 1A progenitors. Range masses is just gathering around 0.15 and 1.25, and also an average values is around 160 to, I can say, the 1.8. And I just like was mentioned, the 1.4 Chandrasekhar mass, the upper limit of being white dwarf, like as definition, and their stellar radius and 0.01. This is the majority that I'm giving, and they crystallize as they cool down. When you just like look at these pictures, you can see they are so faint, and its detection is going to be just like so difficult because they are fading away. They are cooling down, cooling off, sorry. And also you can see this nice just definition of stellar graveyard. This is the carbon oxygen white dwarfs where it's located here. So their new form as hydrostatic equilibrium is shaping its new form. Exactly. So if it is just it's too massive, it becomes neutron star, or either neutron star or black hole. What is happening exactly white dwarf inside is a finest gases and hydrogen, a thin hydrogen layer, and oxygen and carbon, sometimes an oxygen and neon is here. So the quantum mechanics come to the scene. So there's no more exactly ideal gas law is working in through here, and electrons, because degenerate matters, electrons, electron degenerate matter is taking place inside. So this is electron radiation pressure exactly keeps them in shape and avoiding collapsing the star. This is we know this ideal gas, but ideal gas is not working in this type. So because density is too high. This is the ideal gas, and you know from maybe just a high school physics, and everyone knows it. But for white dwarfs, it's not working exactly. And I just like put this slide, what is exactly happening, and the reminder hydrostatic equilibrium. So what is happening? The degenerates gas law, and it's packing up many electrons into tiny volume, and its degenerate matter is independent of the temperature. So which means that if you just like put a pressure on a degenerate matter, it's gonna get smaller, and then it's gonna be just like more massive. So if it is more massive, it's getting smaller. It's acting just so strange. So, and then that's why quantum mechanics is just explains this with Pauli exclusion principle, Heisenberg uncertainty rule and law, and then after that an electron degeneracy rule. So all of them is just a quantum mechanics. And we can also just like Chandrasekhar limits. I also just mention about it. If it is this Chandrasekhar limit is just to determine the white dwarf mass, and then over this mass is collapsing. So these are the characteristics, and there are different type of, this is degenerate A type, degenerate B type, according to spectral classification. Sometimes we put a suffix, and this suffix meaning is here if it is magnetic, if it is just polarization detectable, or without polarization, if it is peculiar or unclassifiable, or just if it is, we don't know anything, we just like put question mark. If it is V, it's just a variability. So if you put a V here, DAV degenerates A-type variable stars, and which is ZZ Ceti stars, that the last discovery about the ZZ Ceti stars. This is stellar structure of different type of what is happening. This is DA stars is hydrogen surface, helium shell. DB degenerate neutral helium surface and nearly pure, and carbon oxygen core. DO is ionized helium surface, and you can see just a PG and 1159. It means that the EWV type of stars, also exposed core of carbon and oxygen. So this is really complicated and complex stars. It's also here properties and different families and listed in this publication, Corsico et al. 2019. It's a very nice paper, and you can see the exactly the real properties and with the real observations. There's also here another nice illustration, and these are variable stars in on a different pulsating white dwarfs. These are crucial because I can understand with the forward method what is happening in the regarding layer. So by using astroseismology. And let's go to just call that a dim stellar corpse, or it's a horrible definition, or diamond, we can say. So what is diamonds that on Earth? And I just checked, and because I'm not in mining industry, I'm not just chemistry person. So diamond structure is just allotropes of carbon. It's a graphite structure and diamond structure. And then I found this information. So it is inside exactly what is happening is inside the stars. If it is pure carbon, exactly what we know about on Earth, it's diamonds. So solid carbon comes in different forms on allotropes, depending on the type of chemical bonds. So they are just like with the different chemical bonds, we call them in different names that I found. So this is what is happening. It's a cooling process and make them crystallize. So cooling sequence and crystallization, how it is happening in, and this is the latent heat, because latent heat, it's not changing the temperature. You can just like check from the physics knowledge and what is latent heat. It's independent from the temperature. It's just the phase is changing, exactly what happens in white dwarfs. So phase is changing, it's cooling off, and nuclear reaction stops, and there is no reaction and it takes 10 billion, more than 10 billion, completely just a cools off process. So this is another nice, and we are coming to an end to this crystallization, what is happening exactly. So as I explained, is the latent heat. And you can see, I would just like want to show you one animation regarding it. So is a Sheng et al. And by using the Gaia DR2 data is a very good and new discovery. Just comes to, there are two types of, they discovered two types of white dwarfs. And then they called at, there's some of the white dwarf cooling tracks and piled up a just branch, and they called as a Q branch. So which means that these white dwarfs and enjoying the slow aging process, which means that delaying the process. So according to the theory, as a white dwarf crystallized and its particles assembling into lattice and latent heat is released. So it's an aging process. So we can see, sorry. Yes. Look at the Q branch is here. This is a white dwarf branch that as I saw from the stellar evolution, and then this is Gaia data. And Q branch is like a flattish, let's say, like the line. Now, all some of the stars here that just belong to Q branch is piled up here. These are delaying the, you can see the other normal white dwarfs is cooling off in expected time, but these ones is just slowing the process. This is also another theory that like they propose it. It's not a carbon oxygen ones. This is an ultramassive, must be just ultramassive ones, because as another element is come to the scene is a neon. So oxygen neon composition makes them, maybe just they say that theory just says that it's delaying the aging process. So this is amazing discovery as well. So what's going to happen? The first evidence is, are there really just like the diamond stars that exist? Yes, and they are exist. And then if you check, and then diamond in the skies, so you're going to just see lots of media articles regarding this, and diamond in the skies, and there's a pure carbon, something like that. And this is a V886 Centauri or BPM 37093. As an ordinary white dwarf stars and 50 light years away. And that's why my title was a Zillion. It's a 10 billion trillion carats. So instead of saying and repeating of this, and I just like chose the Zillion. So it's impossible to just weigh them. So just a Zillion carats must be enough to define them. So approximately 90% of mass and had crystallized, which is the first evidence to the stellar evolution theory. Their theory even came up 1950s, and it is really amazing discovery. So other diamonds are waiting to be discovered, and maybe just they still just cooling off, and we as our telescopes just make them as a, just our resolution is going to get bigger and bigger. We are going to make them visible. And also, I'm just ending this topic. I hope it wasn't boring, and I would like just like take your attention on this special targets, and rather than it's more special than black holes. And thanks a lot for listening to me. And as today's motivation is, if you are just over just like oppressive the work stuff, and think about diamonds and their pressure, so your pressure is gonna be just less than theirs. Thanks a lot.
Thank you very much for that very interesting talk. I think at this moment I'll invite questions, comments.
Yeah, I've got a comment. I think that diamond is called, that star's dwarf is called Lucy, and
Yes.
I think it is in Centaurus, deep in Centaurus, I think.
Yes, it's a Lucy is a Beatles song, but I little bit like avoid saying this because there are also debates on Lucy as like they mean that as not the daughter of one of the members of Beatles, and it's a drug. That's why Lucy in the Sky.
Yeah.
Just like this little bit certain, and I avoid it. And what I'm doing is I'm advertising drugs or what, and then let me avoid putting the Lucy in the sky.
Yeah. No, thank you for the comment. Is there anybody who wishes to ask or comment some more?
Mr. Chairman.
David, please come in.
Okay, thank you. Thank you very much, Dr. Ulusoy, for the talk. Much appreciated. Just 2 points I'd like to ask. One is that one of the diagrams is called a Gaia HR diagram.
Yeah.
Now,
Yes.
as I understand, Gaia is a feedback mechanism. I'd like to know why that word is used. And the other question I have is, did you equate white dwarfs to dark matter? Thank you.
Yes, white dwarf also just like because it's I said nuclear is a cosmochronometer, and nuclear synthesis is gonna just like show us, if we do nuclear synthesis of the white dwarfs, it's gonna show us radioactive decay of the primordial time, so Big Bang universe, which means that as the progenitors of dark matters, like that the existence of dark matters and dark matter identification methods also is going to just like this star is going to be helpful. And for Gaia, Gaia is just a mission in 2013 launched. It's a satellite mission, and also it's using astrometry method as a positional astronomy, so which means that a parallax. So if you use parallax, it's a certain precision, and you can observe the stars, and you can in Gaia observes till now just a 1.7 billion stars. So with just a 1.3 billion is high precision. So which means that if you dot these stars with the same, they filtered with the same, similar to masses, just with the sun and chemical composition. Gaia also gives you effective temperature. Gaia also gives you luminosity. Gaia also gives you just a spectral features of the stars. If you collect this information and mapped on a diagram, and the information is amazing. So thank you.
Thank you very much.
Okay, thank you very much for the question and answer. Do we have any other comments? Questions? It looks like everybody is. Oh, Rodri.
Yes, I had a quick question.
Okay.
Ceren, what are the main pieces of evidence that the star the white dwarf you mentioned in your last but one slide, has crystallized into diamond? What's I can understand the theory of why we think they would crystallize into diamond, but what observational evidence do we have that that's particular object which you seem to be putting forward as?
Oh, sorry. There's a chemical exactly composition they just released out, and it says that carbon oxygen phase diagrams and shows us that crystallization is real. So it's not completely crystallized, which means that exactly this is the first evidence is giving us, okay, we are going through in the right direction, which means that and crystallization is started. So is a chemical composition and carbon oxygen rates and is determine actually the rate of crystallization.
Okay,
as far as
thanks. Yeah,
thanks.
Okay, that makes sense.
Yeah.
Thank you very much. Are there any other questions, comments?
Mr. Chairman,
David, come in.
can I ask something that's got completely nothing to do with this talk? Could I ask Dr. Ulusoy whether what sort of outreach to schools and things like that EOS does?
So recent outreach.
Yeah, to schools and to astronomical clubs within schools.
Yeah, so far actually, because of the COVID, that 2020 and 2021 was dead, but the last year, some schoolgirls and coming from the high schools and they visited BUs, and then I actually gave them a seminar regarding the astronomy topics, and plus in June with Prof. Fulvio, and we received that exactly just nice funding from International Astronomical Union, and we are going to southern Botswana, visit Mochaba, I think so is the school names, and we are going to actually just make a real outreach professionally. And International Astronomical Union is going to support us. So this, for the time being, what I'm doing is.
Thank you very much. Maybe I'll be in touch with you. Thank you.
Yes, please. Yes, I'm open. Welcome.
Thank you. Yeah, I think ASB will be very much interested in your activity. So are there any, Rodri, is that an old hand or a new hand? Rodri?
Sorry, yeah, let me take it down. Sorry.
Okay, all right. Well, I'll take this opportunity to ask my own question. Yeah, I think I may have missed it, but I would like you to comment on the temperature. You know, that these white dwarfs can be seen. Oh, I would like you to comment or to say something about the temperature of the white dwarfs, because you know, if it's a crystal form, one doesn't expect an extremely high temperature, and perhaps comment on, you know, at what temperature can you actually see a white dwarf before it becomes a black dwarf. I've finished.
Can you hear me?
Question.
Because
oh, you can't hear me.
Sorry.
Oh, can you hear me?
It's my internet connection, or just I don't know. Just sometimes it's just unstable. It's
okay. I'll repeat my question. I would like you. It must have been in one of the diagrams, but I would like you to comment on the temperature of the white dwarf. Simply because it's existing.
Okay, I can.
Form. Yes. And when does it stop being a white dwarf to become a black dwarf?
Just temperatures, like if we think about our sun's temperatures, the surface temperature is going to be 6,000 Kelvin. So almost, and but for the it depends on because as star ages, temperature is changing and brightness is changing. So that's some turn-off points when the hydrogen finished, like completely just turns to helium, it's going to be temperatures, the red giants, and then we are gonna see just like in bigger temperatures, and in the stellar core and a sun, 10 million Kelvin, 15 million Kelvin. So the stellar core is a 15 million Kelvin. Even a planetary nebula is going to be X-ray just sources. And imagine the energy is too hot, temperatures are too high. And it takes, and according to calculations and theory, even more than universe age, the cooling down completely. So more than 13.7 billion years. And it's going to turn to black dwarfs. So in the universe, there's no black dwarf exists. We don't know any because they are not shining. They are not sending lights. So that's why they are so important.
Oh, okay. No, thank you very much.
Welcome.
Are there any other comments? I think at this point, I would like to thank the speaker. I think, yeah, this is really enlightening. I specialize in what happens in the interior of the Earth, and when I compare with what happens out there in the star, it looks like a very interesting comparison. So thank you very much. I personally have enjoyed this very well, and I'm sure I speak for the audience who have. I can see nobody really left the talk, so I can see that they've really been interested. So thank you very much, Ceren, for that excellent talk.
Thanks, Ceren.
Thank you, Michael. Thank you.
So I think at this point we can end the event. Yeah, I think the committee is getting ready for another meeting. So thank you very much, Ceren.
Thank you. Good evening. Evening, everybody.
Good evening. Good evening, Mike. Okay.
See you soon. Bye. Bye.
Bye.